So, welcome back. This is our week 4 first lecture, right? Talking about fossil fuels, right? Burning dinosaurs, as it were. Covering a few of these details a little bit more specifically, what's actually happening with them, right? Not to damper on the fun too much, but we do want to take a little bit more of an informed approach about this. Before we do that, though, you might remember at the end of the week 3 lectures, we ran into a little bit of an issue. I had more slides than I had time to talk about them. But that's, I think, a pretty alright thing because they play very well into some of the things that I want to talk about here. I'd rehash details anyways, so this is a good time to talk about it. Some of these things we did talk about last time, right? Things like energy quality, understanding the difference of these different features that we're looking for in different energy sources. Not to say that this is necessarily a hard number, right? We can't necessarily compare any of these as particular values. Really what we're trying to do is we're trying to look for some type of energy that does a good job with all of these conditions. Right, that's really what we're looking for. There's not any one specific thing, right? You could argue here that the teaspoon of gasoline is significantly easier to transport than the 2-ton car, right? And I think I'd agree with that, right? In the majority of cases, it is significantly easier to move that teaspoon around. But how we can end up using that gasoline is really only to create thermal energy, where the car, that's kinetic energy, mechanical energy specifically, that we can use to transport into other forms. So all of these different types of energy have their own benefits, have their own detriments, and the energy game here that we're talking about, the quality of any single energy source, is really how well does it satisfy these things? Is it doing the thing that we need it to do well? Or is there something else that could be doing it better? So, a little bit tangentially related to that, the laws of thermodynamics are what govern a lot of how we consider heat engines. So there are technically 3, and then we call it a 0th law of thermodynamics. We're not going to worry about those others. Right now, we just want to focus on the first and the second. And the first, I'm sure you're actually already familiar with, right? It's a very commonly known idea at this point. It's conservation of energy. Energy can't be created. It can't be destroyed. It can only change forms, right? So if I wanted to, for example, slow down this 2-ton car, that energy is going to have to go somewhere. I can't just get rid of it, right? When the brakes are applied to this car, there's friction, there's, wearing on the brake pads, there's heat, there's sound, there's all of those features, and that's really where the energy is going. It's starting from one form, transforming into another. So that's all that the first law of thermodynamics is really trying to say. When we're thinking about thermodynamics, we like to split this up into 2 specific categories. That is, the thermal energy of any sort of material that we're looking at here can be changed by either adding or taking heat or adding or taking work, which, if you remember, our definition for that was some force over a distance. So either one of those two, I know we most frequently think about heat, but work is another way to change that energy. But at the end of the day, again, any give or take that is just transforming from one place to another. So the second law of thermodynamics is a little bit more unique. What it's trying to do is it's trying to talk about entropy. And entropy is one of those things that it's really hard to give it a concrete definition. I'll admit, nobody, there's a famous quote about using the term entropy in certain types of machine learning. And the reasoning is that, for one, it sounds very smart if you're saying entropy when you're talking about machine learning. But for 2, if somebody tries to question you on it, they won't be able to because nobody understands what entropy is. But we do have a kind of working definition for it. Entropy is a measure of chaos or a measure of disorder in a system. So we can imagine a couple different scenarios. Right, let's imagine that you have a totally sorted out deck of cards. Let's say, for example, it's hearts, diamonds, spades, clubs. Every single card exactly in order, starting with ace, going all the way to king in each suit. That is a very well-ordered system, right? 52 cards all in a very, very specific order. But now, let's say I play my favorite game, and we play a game of 52 card pickup. And not only are we playing a game of 52 card pickup, I throw it on the ground, I spread them all around, and then I close my eyes and I pick them up and I sort them all out again. What is the likelihood that when I pick them back up after they've all been scrambled, that I'm going to get to that exact same ordering? And there's actually a number for this. If you imagine every single atom in the universe, take away the hydrogen, right? That's the most common one. So everything heavier than hydrogen, every single atom in the universe besides hydrogen, and the vastness of space that it is. Your odds of picking up that stack and it being in order again are less than 1 in the number of atoms in the universe, minus hydrogen. That's a substantially small number. There's not a good way to really conceptualize that, if I'm being completely honest. If we think about even like a particle of dust, if you see a dust bunny, you know, if you haven't vacuumed in a while or if you haven't dusted in a while, that right there is already billions and trillions of atoms. If we're talking about 1 gram of water, that's already some 10 to the 23rd atoms, actually 10 to the 24th atoms at that point. So when we're looking at the vastness of space, the number of atoms that exist out there are so incredibly high that it's a meaningless number to me. I can't comprehend how big that number is. I can't even stack it up against anything. But somehow, a deck of cards, just because of how many different possibilities there are, it's extremely unlikely that you're going to pick it up and it's going to be ordered. Right? There's actually an extremely high chance, if you shuffle a deck of cards, and you actually shuffle a deck of cards, that that particular order of cards has never existed in history ever before. Because there's just so many different possibilities. So that's kind of this highlight between a very low entropy high order system and a very high entropy low order system. Right? I'm expecting that when I pick up the cards, they're scrambled in every which way. Another example you might consider. Imagine, look around at the room that you're in. Imagine one corner, just a tiny little corner of that room, has 200 degrees Celsius. Right there, nowhere else. The rest of the room is at perfect room temperature. That is technically possible. Right? There's a wide distribution of temperatures of all of the different air molecules, and technically, it is possible that all of the highest energy air molecules suddenly find themselves in one particular place in the room. But how likely is that to happen? It is exceedingly unlikely to ever happen, right? I have never walked into a room and suddenly had my face boiled off because there's just a random hot pocket in the room. It just doesn't happen like that, right? Because the air molecules are in a relatively high entropy state. That is to say, they're never going to just suddenly condense into a high order system. They're already chaos. They're already disorder. They're not going to suddenly refine themselves in order. And that's just the way that the universe goes. So this is a difference between what we call reversible and irreversible processes. Mechanical energy is oftentimes a very high quality energy because many mechanical operations are reversible. If I lift up a block and drop it, all of that potential energy, or 99% of it, we lose a little bit, but 99% of that potential energy gets turned back into kinetic energy. So that is a very transformable process, whereas something like thermal energy is not so transformable. Right? If I start with one hot side of a room and one cold side of a room, then eventually everything is going to coagulate together into kind of a medium temperature all the way around. But it's extremely unlikely that it would sort itself back out. So that would be considered an irreversible process, letting the room come to some middle temperature. And that irreversible process is what entropy operates on. Entropy always increases because the universe is always going to get a little bit more disordered. It's very unlikely, at least on a grand scale, that things are suddenly going to order themselves a little bit more. And that has some other consequences too. more specific to physics, but there is one that we will need to highlight here. But put a pin in that, we'll come back to that idea. So, talking about what nature would naturally want to do, temperature is going to be some sort of indicator about how heat is going to move. Right? If I have a high temperature area and a low temperature area, and I allow them to communicate, allow them to transfer heat, then every single time, heat is going to go from the high temperature to the low temperature. Likewise, if you imagine a dam on a river, once that water reaches the top of the dam, it spills over, right? It naturally happens. What if we put a water wheel on that dam, though? The water still naturally going to fall, but now we extract some useful energy out of that process that's already going to happen. That is exactly the thinking behind a heat engine. Heat is already naturally going to flow from a hot area to a cold area. So we put in a thermal water wheel, in a sense, that is the heat engine, to extract some of that natural process and pull energy out of it, energy useful for us. Now, there are a couple different ways to do this, right? Heat engines can be split up into either internal combustion engines or external combustion engines. The externals, of course, are typically much bigger. Sometimes you can get a higher efficiency out of them, but they are not so practical in smaller form factors like cars or household generators. So still very useful, still used. Not all of the old external combustion engines are in use anymore, but some of them still are. But generally what we'll do is we'll talk about this hot reservoir, we'll talk about this cold reservoir, and we talk about there is some useful energy exiting the system, right? That is our wheel, our thermal water wheel, able to pull some of that energy out. But one thing that I do want to highlight here is that this waste heat idea, this is actually a necessity. Any heat engine will have exhaust. You can't ever extract all of the energy, but I'll talk about why. Again, that's the pin that I was talking about before. We'll get back to that in just a minute here. More generally, efficiency, we can calculate this. What this is our useful energy divided by how much total energy did we have to put in. QH, this is our total energy that came into the system. It gets split into these two branching paths. All of the useful energy, all of the exhausted heat. Energy conservation does still apply, so everything that comes in must also come out. But this is how we talk about efficiency. So, what we found, to go off on a little bit of a tangent here, is that for a lot of these power plants, what we would typically do is we would put these things frequently on a river or by a lake or something like that, a large water source. Because water, we talked about this before, right? Water has a lot of room. It can take a lot of energy into it before it starts to change its temperature. So using that water, we would help to cool our plants. That would be where we would spill that exhaust heat. Problem was, the water that we put back into that river, back into that lake, was 5 to 10 degrees Celsius warmer. And it turns out, plants don't like that, fish don't like that, birds don't like, nothing likes that. Nothing is happy when we raise the temperature by that much. It has actually a lot of very significant adverse effects, and it can very quickly start to destroy ecosystems. They're just not designed for that sudden temperature change. They're not expecting that. That can cause a lot of issues for them. So the EPA did make this illegal to take it directly out of the power plant and put it directly back into the river and or lake. They have to go through some sort of cooling process first. So if you've got it in your mind, if you think about like a nuclear power plant and you have in your mind those giant cooling towers, that's not actually where the reactor is. That's where all that cooling is done on the water. Many modern day fossil power plants also have those cooling towers at this point, right? It's just a necessity to make sure that the water is a reasonable temperature before they put it back into nature. So what I want to try here, actually we already did this last time. Never mind, we'll come back. We'll look at another problem here soon, but we did talk about this a little bit last time. So that pin that I was talking about before, right? How we always have to have some sort of exhaust energy. Unfortunately, entropy still has its hand in this as well. So a very famous physicist, Carnot, He was studying through some of these consequences of looking at our thermodynamic laws and thermodynamic equations. And what he realized is that there is actually a certain degree of order associated with heat engines, to the point that even if you create the maximum possible efficiency heat engine, you still have some waste heat. There's still exhaust that comes out. There's no way to stop it. And in fact, the efficiency of your heat engine has an upper limit based on the hottest and coldest temperatures that are on that engine. So that is to say, our hot reservoir, our cold reservoir, right, when we're thinking about where we're pulling this energy from, where we're sending it to, that is actually a maximum cap on our efficiency. And we talked about this a little bit before. The only way to get 100% efficiency is if you take this T cold to absolute zero, which is not possible, or you take your hot temperature up to infinity, which heat engines are not going to survive at infinite Kelvin degrees, right? It's just not going to happen. So we're always limited to this. We're never actually going to achieve 100% efficiency, but this does give us a kind of a number to compare different engines, right? There are different feasibilities. Now, few engines actually hit this efficiency, but it does inform us of just that upper limit in the first place. So we can reverse a heat pump as well. We've talked about this a little bit. This is what a refrigerator is. Or again, if you've got an updated infrastructure for your air conditioning, a heat pump is doing this exact same thing. It's just a heat engine working in reverse. So it's actually pulling heat from an already cold place and spitting it out into a hotter place. And that seems a little bit counterintuitive with what I've been saying, but as long as we put in some extra work to make that happen, it is doable. And the number that we use to compare these refrigerators or heat pumps is not actually efficiency anymore. It's a value that we call the coefficient of performance. But it's still serving very much the same purpose, right? It is how much energy are we extracting? What is our, how much are we achieving towards our goal versus how much did we have to put in to achieve that goal? So I've got some repeat slides here, unfortunately. But we can look at this problem, right? So let's read through this for a minute. A combined cycle power plant, and that's actually specifically, this is kind of like two engines put together in one. So when they burn the fuel, the hot gas from burning of the fuel, they use that to push one set of turbines. And then the waste heat from that first one actually goes into heating steam to be driven in a second turbine. It's a way to get a little bit more efficiency out of your heat engine at the cost of, it's a lot more expensive, right? At the cost of actual dollars kind of cost. It's more expensive, a little bit more difficult to maintain, not quite as simple, but it is higher efficiency. There are some places that do use these. But anyways, that's a tangent. We'll come back to that soon enough here. Let's imagine we've got these two temperatures. We've got a maximum temperature of 1080 degrees C and a lowest temperature of 10 degrees C. So what is the thermodynamic efficiency limit, right? That Carnot efficiency. So assuming you're pausing the video, coming back now, let's talk through this one. So as I'm seeing this thing, one thing that I will warn about, if you are finding inefficiency greater than 90%, you need to take one more look at your numbers here. Because let's go ahead and take a look at that equation one more time and imagine some different scenarios. What if I plugged in negative 10 degrees Celsius? Suddenly, I have an efficiency greater than 100%. Energy conservation says that's not allowed. What that actually tells me is that Celsius is not the thing that we want to use in this equation, right? There's a reason that physicists love Kelvin. It's just got so many different uses, right? It's pretty universally applicable. Instead, what we need to do is we need to convert both of these temperatures into Kelvin as a first step. So my cold temperature was 10 degrees Celsius. That is now going to be 283 Kelvin. My hot temperature goes from 1080 to instead 1353 Kelvin. Now we plug in the Carnot efficiency, so 1 minus this ratio, and what we get is an efficiency of 79.1%. So super high efficiency theoretically, but real heat engines might not necessarily get that high. So a fantastic example of an external combustion engine is old locomotive trains. Right? We had the coal truck right behind them. They would shovel coal into the burner. The burner is going to heat up all of this water into steam. Steam drives the cylinders that actually makes the whole train go. And then the last step of this is that they actually need to cool that water back down, right? Because again, we're running into a Carnot efficiency problem. If you never cool down your water, then you can't achieve efficient engines anymore. You need as big of a temperature difference as possible. And you need to cool that specific water because when you're on a moving train, it's hard to get more water, right? It's typically not built next to a river, not built next to a lake. We can't just scoop it out and pour it into our engine. So any water that we've got inside of the engine, we have to be working with that the entire time. So typically, we've got the massive boiler that's going to make this very, very hot. It's going to drive the cylinders, and then it's going to go through the outside, try to cool with the outside air as much as possible to bring that temperature way down before we start the cycle all over again. Modern power plants, right? They're, of course, a little bit bigger, but working with steam still turns out to be one of the best things that we can do. Largely because, if you remember, water has such a high specific heat, and steam also has that very high heat of transformation. Those two things together mean that it takes so much more energy to actually raise them up to those temperatures. We can put a lot more heat into those before we actually use them to transfer that energy to drive our turbines. Steam engines are some of the most efficient engines that we have right now, right? They are very, very, very common to see. But in any sort of power plant, not even necessarily just a fossil fuel power plant, you start with water, you've got your fuel burning, generating heat, it boils that water into steam, the steam turns a turbine, spins a generator, generates electricity. That comes back into a condenser system that condenses that steam back into liquid water. Sometimes this is an open cycle system, so that is the cool water, there's not like a wall right here. What it is that cool water comes in from some outside source, goes through the process, the hot water sent back out into our river, lake, ocean, wherever, or into the cooling tower, now with our regulations. But sometimes it's also a closed system. You know, they might not use water, or they might use a special type of water, something else like that. So whether or not it's an open or closed system can be a variable, but either way, this is the full process. And this is that again, but with some, it's a little bit hard to see if you're just looking at this thing. I'd recommend downloading the slides, but these are what all of these individual pieces look like. If you actually look at what's going on with any sort of power plant, you can see these different pieces in operation. And in fact, we had one of these right on the Ohio River, and in fact, we actually didn't have just one, we had 10. 6 of them were coal-fired power plants, 4 of them were oil, but we can see a lot of those features here, right? This is specifically down here at the bottom. I'll do a different color so we can really see it. We've got a grading where that river water comes in, right? That's our cold water intake. Goes through the whole process, needs to be cooled down a little bit more, and then sent back out into the river right on its way. We've got the smokestack, so we can see where it loads, the hopper that's actually getting it into the whole power plant. Emission control precipitators, really that's just a filtering system is what we're trying to say there. But that's what it actually looks like. And this is actually not working anymore. This was shut down in 2014. I know that somebody else has bought the land at this point. I don't know if they've torn down the old power plants. I think they're wanting to do something else with this land, but I don't know if a project has been started yet to do anything with it. So that's all about how we actually use the fossil fuels. Let's talk about how they're actually formed. Generally, first step, something has to die. Sorry, that's the way it is, right? Plants, plankton, not frequently animals. Animals don't usually make good candidates for this, but it's mostly plants or plankton. But all of these living things are composed of very, very useful hydrocarbons, right? Different chains of carbon, hydrogen, oxygen, nitrogen, other things like that. When something dies, it's going to go through some sort of decomposition process. And that decomposition process will change very much whether you've got oxygen or not, right? Just like with aerobic respiration, bringing oxygen into the equation means that there's a lot more energy release, means that the decomposition is really going to kind of rip apart whatever was there before with those hydrocarbons. Oxygen, after all, is a very reactive chemical. So the aerobic stuff is not what we're after. Instead, the anaerobic, without any oxygen, means that oxygen can't come in there and liberate all of those hydrocarbon chains, right? Any energy stored in those hydrocarbon chains stays right where it is. Other stuff dies out, right? But it condenses over some period of time. And the first step of this, at least when we're talking about plants, is actually starting to form peat, which is a really, really common material. In fact, if you've ever had any sort of reptiles as pets, you might have used something like peat moss as the bedding for them. It is not very old dead plants. Dehydrated at this point, clearly dead, pretty flammable, but not super old. Not yet, at least. But you might start to realize here that all of this energy, it must be coming from the sun. At the bottom of every single food chain are plants. Whether it be phytoplankton in the ocean or ferns or anything else like that. But plants are generally the first step of every food chain. And going up from there, any energy that the plants absorbed from the sunlight gets transferred onto the next species that eats it, and the next species that eats it, all the way up the food chain up to the very top. All of it is being powered by the sun. So one way that you can think about fossil fuels is that it's really kind of like a power bank of stored sunlight. Sunlight that hit the Earth millions of years ago was absorbed, captured, stored away underground, and now we're starting to extract that to use it as fuel. Even to the point where you can see some dead plants in low quality fuel. The better the coal, the less you're going to see fossils in it. But what we can do with this is generally a photosynthesis process is taking carbon dioxide, water, and energy, combining them all together to form those carbohydrates, those energetic carbon chains, and oxygen. If you burn that result, if you introduce oxygen back into it, you get energy back out. And that's exactly what we do with these things, right? Typically, we're burning fossil fuels. So I'm going to split this up into a couple different categories here. Let's first focus on coal. Coal actually has a pretty historied use. We've used it for a very long time. I don't know exactly how we stumbled across coal. I have to imagine that early humans were just walking around with fire. And I guess not that early humans, right? It's not that long ago, but they were just kind of walking around with fire, holding it to rocks, seeing if anything happened. And eventually they found some rocks that actually caught on fire and kept burning. So that must have been a little bit alarming. But we've been using coal for a very long time, mostly for metallurgy. The very high temperature that it burns at is useful for warmth in some sense, but long before that, we would find cool rocks out in the field, and we would see some shiny bit that we were interested in, but it wasn't really holding together. It wasn't refined, or it was split up into multiple pieces. And by introducing coal with this, we would bring it to a very high temperature, we would liquefy it a little bit, we could combine it, we could refine it, and we turned it into swords, right, among many other things. But humans like swords pretty well. We made a lot of those. Sometimes we use it for writing, sometimes we've used it for a couple different things, but that's been a lot of it. It wasn't until the Industrial Revolution that it really saw the use as it has been today, right, where we went from using that for making nice refined metals to really ramping it up for generating electricity. In the 1830s, we started doing a little bit of that in the USA, of mining that coal. So the question is, how does it really form? Well, we talked about it starts with peat. And generally, when we're talking about coal, this is forming in what used to be swamps. Swamps are a fantastic place for this, right? Because if something dies in the grasslands, well, then it falls onto the ground, oxygen gets to it, aerobic decomposition, nothing left for us. Unfortunate, but in a swamp, something dies, falls into the water. Oxygen is not able to get to that. And if there's slow-moving water, suddenly sediment, sand, dirt are starting to cover up that decomposition, so even less oxygen can get to it, right? You might have heard grim things like bayou bodies from horror stories or anything else like that, bodies that just didn't decompose because they were trapped in a swamp. So first, when plants die in that swamp, or sometimes animals, but mostly plants, they die in that swamp, they fall into the water, they don't decompose with oxygen. Instead, they kind of all start to form together. When we start to add a little bit of pressure, a little bit of heat to this, it starts to form solid rocks. And that is our first step of coal that we call lignite. And lignite's not a super useful type of coal. It's not very pure. It doesn't have a ton of energy. It is generally only used for power if it is close to the location, right? So if we don't have to do a lot of transportation, then it's a really appealing thing. Otherwise, not super good to have. But if you wait a little while longer, add a little bit more pressure, add a little bit more heat, you start to get to bituminous and subbituminous coal. And these are, I think, the main types of coal that we typically see, right? They're the big ones. They're the majority of coal. They're fantastic for electricity production. They've got a little bit of a higher energy content. They've got fewer impurities. It's a little bit better all around. If you give it long enough, eventually that coal will turn into anthracite. And anthracite's really special because it's, for one, got the highest carbon content, right? The highest energy, the lowest impurity. And that means that it's got some special uses. For one, it's a little bit safer to use around people because it burns cleaner, right? We don't have as many impurities like sulfur coming into play. It's not going to produce as much smoke that's very dangerous. If you ever use anything with a carbon filter, so thinking of like furnace filters or aquariums, that is probably actually powdered anthracite being used in that. Sometimes, depending on your country, this gets used for power plants as well, right? If we're talking about places where regulation is a little bit higher, but they still need coal for whatever reason, anthracite is probably the one they want to go for because, again, it's cleaner. But there are not a ton of different places that can actually extract anthracite. So bituminous and subbituminous are the primary fuel sources that we use for things like electricity or, other things that are going to need coal like steel. So these carbon chains, these chemical equations that I'm giving you here, this is telling us a couple different things. For one, it is telling us the length of the carbon chain. The longer the carbon chain, the more energy is being stored in there. But for two, it's also telling us something about how frequently those impurities are showing up. Nitrogen, not a big deal as an impurity. That shows up in a lot of different places. That's pretty common. Sulfur, though, that's a little bit more dangerous. That's one that we really don't want in our fuels because breathing in sulfur is not fantastic. So the more carbon and hydrogen we have relative to the sulfur content, generally, that's going to be a better place to be. Here's just a little bit of a chart. There are subcategories for this, but generally, this is just not stuff. If you're working with coal, you might want to be a little bit more familiar with these, but, I'm going to assume here that we are not all coal miners or coal workers or anything else like that, but it is kind of interesting if you want to see roughly how all these things start to break up. This is what the deposits look like in the US. Right, so again, highlighted in yellow, bituminous, that is our most common type. We use plenty of that stuff. There's plenty of it as well. It's pretty clean, has a lot of energy per coal brick. Very nice to have. There's a couple places where we can get anthracite from, but not nearly as many as that bituminous and subbituminous. Just kind of spread all around the area. There are 5 major basins in the US where we extract coal from. And you can kind of see the trends. This is 2014 to 2018. So if you'll notice here, 2014, 2015, 2016, all the way out to 2018, how those trends have been changing over the years. And pretty well, it's been mostly declining all over the place. Largest reason being, coal's just kind of falling out of favor. There's not a lot of features that make it better than something like natural gas or oil, not better than renewables. It is nice in some places where you need an immediate turnaround. You need to set up a power plant now and you need to get electricity generated, then it's a pretty good place to be. But the US at this point has pretty matured infrastructure, in some places a little too matured, but for the most part, it's just not feasible, right? What we can see from something like this is that even just from what we are producing, what we're pulling out of the ground, there's less demand, so we're pulling just a little bit less. It's just not growing anymore. More specifically, we can look at productive capacity of coal mines, looking at different types. We can see that's decreasing. This is a little bit of a ranking of these different types, the 4 major types that we've talked about, right? Lignite being the lowest quality. We still do have plenty of it around, but we don't like to extract a ton of it because it's not very useful. But that bituminous, subbituminous make up the large majority. As far as it goes for generating electricity, coal's on the down. And it's not really looking like it's ever going to come up again because, sure, old power plants might still use coal, but new power plants, it's just not economically feasible. There's not a good reason to go into coal at this point. It doesn't have as high energy content, transportation's more difficult, it doesn't burn as clean. Not a good reason to get into coal at this point. There are other sources that are better investments when we're starting to look at upgrading infrastructure. So, let's look at the other flavor of fossil fuel that we're normally using, right? Petroleum. So petroleum, actually, the name of this, the petro part, we're looking at rocks, right? Rocks that have fuel in them in some way. And that's 3 different forms that it can take. There's natural gas, there's crude oil, and then there's actually oil-producing shale, which is like solid rock that has these little tiny pores with the oil inside of it. So to say that we definitively know what this is a little bit untrue, but we are fairly certain that what this is primarily a bunch of phytoplankton, actually. Phytoplankton, other types of plankton, they make up a very significant portion of all of the carbon life in the ocean. So they die in very large numbers. They fall to the bottom of the ocean floor. Those constantly shifting sands means that they get covered up, and they go through a very similar process as to what we saw in the swamps with coal. Right? Over time, this forms a rock layer. It's not able to go through any sort of aerobic decomposition, so a lot of pressure, a lot of heat. It's just a little bit of a different formation of what's going into this means that we've got oil rather than coal. But petroleum actually has an even longer history than coal does. And most of that has not been as a fuel source, right? Unlike coal, where coal was very early on used for refining metals, oil was not used in such a way. And a big part of the reason is because crude oil just doesn't burn well. It does technically burn, but it produces a lot of black smoke. It doesn't burn very hot. There's a lot of issues with trying to burn it like that. It's just not a very suitable source for anything, right? And we knew that from an early time. We knew it was pretty flammable, but we just didn't use it for any of these things except in very, very specific circumstances. Most of the uses for petroleum were actually medicinal uses. And you might be using some of this stuff yourself, right? Speaking of petroleum specifically, right, many of the plastic products that you used are petroleum-based, right? Not as a fuel source, but as different components inside of the petroleum, they can be refined into other useful things. It's got a lot of medicinal use. If you've ever used Vaseline, that's another petroleum product. So we didn't think it was a very good fuel source, but we had a lot of other uses for this chemical. And sometimes you would see these kind of like tar pits, these oil pits where just a little bit of oil was leaking to the surface. Actually, at the time, it used to be a contaminant to salt mines before we really knew what to do with it. And we'll get to why that is in just a little bit here. But you can see kind of a fun comparison. In 1859, we had our first oil well in the U.S. that was actually established, and they very nearly stopped. They had more of a hunch than anything that there was oil where they were drilling. And right before they were about to stop, suddenly oil started spilling out of the ground. They really weren't sure if it was actually going to work, but at this point, we started working on refining oil. We realized that we could refine it into, useful fuel rather than just this very poor burning material we know it as currently. And you can really see that start to pick up because just 3 years later, we're looking at 3 million barrels in production, right? So it very rapidly ramped up. How we actually refine that? Well, the most common way is to put it into a distillation column. Here's the idea. Take raw crude oil, put it into a furnace, not to burn it, but to get it very, very, very hot. When it's very, very, very hot, most of it, I shouldn't say most of it, a very significant portion of it turns to a vapor, right? A gas. What doesn't turn into a vapor, that's a bunch of really heavy oil that gets used in other uses. Not suitable for fuel, but good for, I mean, you can see it down there, right? Lubricating oil is one example, asphalt's another. There's a lot of different products that come out of what's going on with that. So the rest of these things, these are all vapors that are now rising up the tower. And what happens is at each individual layer of this tower, the gas is a little bit cooler than it was on the layer below. And just lowering that temperature ever so slightly means that some of the gas starts to condense. Not all of it, right? There's actually a lot of different things all mixed in there together at once. But some of those things start to condense. They form a liquid layer that we can see is getting piped out. And so every additional layer, hot gas comes up, some of it condenses, the rest of it continues on to the next level. And it keeps going up and up and up and up and up until we get back to like room temperature, 20 degrees Celsius, probably a little bit warmer than that, but you know, doesn't need to be that warm anymore. That is natural gas that is never going to solidify, or I should guess liquefy, right? Becomes a liquid. Everything else now, we've got those things nicely separated out into those different layers. So what that actually looks like on scale, I realize, of course, this is some sort of just 3D model of what a distillation tower looks like, but it does give you a little bit of a sense of like how big a human is compared to these things. They're pretty large scales, right? A few stories high at a bare minimum. And then the larger refining production you're getting, the taller these towers often are. But there is an upper limit on those things, right? You don't want to make them too tall, because if you do, then when you're trying to get that vapor up to the next level, sometimes it cools down a little bit too fast. But this is roughly how they're going to break into different layers. And for a little bit more detail on exactly what's happening there, right? This diagram doesn't make it clear how the gas gets up to the next layer. It's a little tiny bubble cap. So what that means, it's a pipe that leads up, and then it's got a little cap over top of it. Some fuel has already condensed at that layer, so all the new gas coming in is bubbles. It gets forced through, it comes to the outside, and that's where, if it's going to solidify, it mixes in with the liquid, it becomes a liquid that's funneled off into its own collection area. If it's going to continue being a gas, then it forms a bubble, pops out, rises up to the next layer, continues, so on and so on and so on. So, looking at specific energy, we've actually already seen a table of this, but now we've got a better name for this. It's not exactly the same as energy density, but again, this is very closely related. Specific energy is talking about how much energy per kilogram of that fuel. And the numbers here are not necessarily the end-all be-all, right? Comparing like deuterium, again, the fusion reactor is not a thing that we have yet. So doing this is not necessarily a fair comparison to put it on this table. Uranium, again, a very, very intense amount of energy per kilogram, but there's also not nearly as much uranium as there is stuff like oil and coal. So these are nice values for comparing, but it's a little bit more important if you're thinking about being a shipping company. Right, if you're concerned about how massive something is, generally what you're going to be looking for is that higher specific energy. Right, and here, again, is another reason why we're looking more towards crude oil and natural gas, because just compared to coal, coal just doesn't have it. 24 is at the high end of things. We're not seeing that in all types of coal, right? The low end is 8 megajoules compared to the 53.6 of natural gas. Natural gas and crude oil more broadly than that is just kind of taking over at this point, if we want fossil fuels for anything. So, let's try this no problem. Let's imagine we've got a fun number on here, glucose, right, compared to these other fuels. How much glucose would you have to burn to match the energy output of a natural gas heater using 5 kilograms of gas? Think about it. Spend a few minutes working on this one. Go ahead and pause the video. Come back and we'll talk through it together. And now I'm assuming you're coming back from this thing. And so there's kind of the joke that goes with this, right? That if you drink a gallon of gasoline, it's going to keep you energized for the rest of your life. Glucose, you probably don't want to eat a ton of glucose. That's just regular sugar. But admittedly, it is human fuel in a sense, right? You can burn it, but it's much better used as human fuel. So the first thing that we need to do, right? We're trying to compare two different fuel sources, but I don't have a direct way of converting this mass. Instead, what I'm going to do is I'm going to figure out how much energy comes from that 5 kilograms. So the units are the hints here. I'm going to take 5 kilograms of natural gas, and I'm going to take that specific energy of natural gas. Namely here, looking at this thing, I'm going to multiply this by 53.6 megajoules per kilogram. Now, if we keep track of these units, kilograms cancels out kilograms. We are left with 268 megajoules. Not our final answer, but a good starting point. Now, the question is, how much glucose are we going to need to get that same amount of energy? So we take that amount of energy, we say, okay, 268 megajoules. Again, we've got to watch with units. So if I divide by 15.55, then I get megajoules per kilogram. The megajoules, again, will cancel out here. Kilograms, that's on a denominator in a denominator. So that flips back up to the top. What we get are 17.23 kilograms of glucose. And there we have it. So to rehash on that earlier point about how salt mines used to have this bad problem with crude oil, here's why. Generally, when we're talking about all of these different locations that might have oil, right? Of course, all sorts of different parts of the world were covered in oceans at one point. All sorts of different things have lived and died in those oceans, fell down to the ground. But that doesn't automatically mean it's a good place to extract oil. Really, what we're looking for are specific locations where there's a high concentration of crude oil. And there are a couple things to look out for. Right? Generally, anytime we're doing this, we're looking for somewhere that is being pooled up. And one of the easiest ways to get that is if there is a geographic fault. Right? So some sort of fault line. This is because of an earthquake, a tectonic plate shift, something else like that. A sudden jutting of these plates together means that everything gets a little bit disrupted. And what it leads to is these little pockets where the oil can help condense. Because generally, this oil is going to be significantly less dense than the surrounding rock. So if it's got some sort of upper cavity, it's going to try to pool in that upper area. Right? So we create this fault, we get this little jut that we can pool a lot of oil into, and then suddenly we've got a spot where we might want to be collecting from. This doesn't have to happen in such a sudden movement. It can also happen a lot more slowly with a fold. This is just two tectonic plates that are slowly bumping into each other and kind of rising up like that. Sometimes mountains are formed this way. But when that process is occurring, right, just over time in much the same way, they start to press into each other. We get this really, really high increase in pressure, and it starts to kind of bubble up. And now that we've bubbled up at the top, that's where the oil rises because it is less dense, and we've got these nice little pockets of oil. And then finally, what'll happen here is that sometimes you'll get these salt deposits in the earth, where it's a large concentration of salt. And just like with the oil, the salt is technically less dense than the surrounding rock. And it doesn't rise nearly as quickly, but very, very, very slowly, that salt does try to rise to the surface because it is just less dense. And that creates, you can see this, a very, very similar feature as the tectonic plates kind of bulging into each other like this. So this is why salt domes or salt mines typically have bad oil issues, because oil tends to kind of congregate around these salt domes. And it used to be a big issue because you can't easily burn it out. There's a number of just a small number of issues when you're trying to actually mine salt like this, where oil will start to get in the way. So nowadays, of course, we have a use for that oil, but back in the day when they were originally mining all of this salt, they really didn't have that same kind of use for it, so it was really seen as just more of a contaminant than anything else. So the question might become, how do we actually find these spots? Well, right off the bat, we can kind of see some of these are features that we can notice geographically. But that's not all we can do. That's going to give us a hint. That's going to kind of localize where we should be looking. But even then, if we're looking along like tectonic faults, we've got millions of miles, millions is probably a little bit of a stretch, thousands of miles to be looking through here to try to find good spots where the oil is. And digging constant wells in all of these locations is not very feasible. So here's what we do instead, right? Instead of trying to immediately drill some sort of well, we explore the area a little bit more. Now, one of the easiest ways to do this, or at least one of the first starting methods that we do nowadays, is we'll drill a bunch of really tiny holes, right? So not to the same depth or not to the same width as when we're talking about actually getting the oil out of the ground, but just, a little bit smaller, just enough that what we can do is we can put some equipment down in these holes, or we can put some explosives down in these other holes. And what we really try to do here is that these vibrations, we have seismographs all over the place. When the explosions go off, they create vibrations. Vibrations move differently through different materials. So depending on the type of rock, depending on if there's oil there or not, depending on if it's really porous, depending on if there's water, all of these are different things that are going to allow the vibrations to travel or reflect the vibrations or do a lot of different features from that. Right? It's a bunch of stuff that I don't do personally myself. It's very complicated. But we'll take all of this data from all these different seismographs all laid out around the area, and we'll compile all of that data into like a 3D map of the density in that area. So, and it's not just one uniform density, of course, right? It's picking out those different pockets of different densities that we start to see in the Earth, and we know pretty well what the density of oil is. So that helps us locate. If we notice that something that has the same density of oil, there's probably going to be oil there. It's not a complete picture, right? There's only so much we can do with this. So typically the next step is that we start to drill in an area of interest and start to take up samples. So this might be a little bit of a wider one, but what we're really doing here is that every single time we drill up some of the rocks, we take a look at those. We look and we see, okay, how much oil is in this thing? Is there any oil in this thing? How deep are we? How hard is this rock, right? Is this feasible? Could we dig through this? Could we look for oil? Do we think it's actually going to be here? And there's a final way to do this that is not common anymore, not by a long shot, not with today's investments, but something called wildcat drilling that, during the initial oil rush was certainly a lot more popular. Nowadays, we don't do it. But it is where you just think that there's going to be some sort of oil there, you drill and you hope. So again, when there was the oil rush, when you could really make it big if you lucked out, maybe it'd be worth it. But I think nowadays, nobody really does this. But, it's kind of fun to consider. So, actually getting this out of the ground. If we go back a couple slides here, we take a look at this. I think it's a little bit more clear, especially when we're looking at the folds, that this oil is actually under a significant amount of pressure still, right? Pressure was used in forming it, but even now there's a significant amount of pressure, right? These things are kind of pushing together, and it's almost like, I don't want to gross anybody out, but it's a little bit like popping a pimple at a certain point, but it hasn't popped yet, right? That's where it's at. There's just an immense amount of pressure here. So when we start to drill into it, if we do puncture a hole, oil does start to spill out. And any of those old classic Hollywood depictions of like an oil well or anything where it's just like shooting out of the ground, that's not entirely unrealistic. Some wells are like that. But we're generally not just kind of like holding out buckets and collecting that as it rains down upon us. Instead, what we're doing is most of the time we're drilling there and then we're setting up a pipe to start taking that back. So how we actually get there in the first place, right? We need to talk about these drills. Typically, we have these very fancy tri-cone drills, but at the end of the day, we run into a little bit of an issue because these are shiny, fancy, refined rocks, but they are rocks, and rocks grinding on rocks just destroys rocks. So instead of just putting them down there without any sort of help, we inject drilling fluid, or we just call it mud. Typically, right? Drilling mud if you'd like, but I think it's just called mud typically when you're talking about it in the field. So there's a couple different reasons that we might want to do this. Some of the biggest ones are generally because we're going to be able to get debris out of there. We're going to be able to keep the drill heads cool, and we're going to add a little bit of extra abrasion that the drills don't need. But then kind of on another side note of this thing, of you don't want to create a large difference in pressure one way or the other, right? Especially if you're about to pop some sort of oil well or anything else like that, you want to make sure the pressure is maintained so there's not a sudden lurching of material one way or the other. So that's another good reason to have this fluid in there, to maintain some sort of pressure gradient so that we don't see a sudden lurch one way or the other. Or sometimes we'll use water, sometimes we'll use oil, not as frequently compressed air, but it is another thing that can work, right? That's especially going along the maintaining pressure side of things. But water and oil are a lot nicer because we can add abrasives to it. Clay, polymers are very good ones. Diamond dust is actually another one because diamonds are very, very hard. Helps to kind of bust that out. So anyways, we shoot it down. It gets used in the drilling, it comes back to the surface, and then it goes into a quagmire. And this is actually kind of falling in line with our small drilling for rock samples, right? This is small drilling for rock samples. We're not just taking individual cores of the rock. That is one part, but we're also looking at what this mud looks like. Is there a lot of oil in this, right? Are we starting to see oil come back out of this? Are we seeing very hard density rocks? You know, do we need to change the fluid that we're actually putting down in there? Do we need to change those concentrations? And we're looking at all of those things as we see them. We collect it, we clean up the runoff a little bit, try to do a couple different things with it to clean it before we put it anywhere else. But that tells us a lot about what we are going through at any given point. Once we hit that porous rock that's got oil, typically we'll try to allow it to naturally flow for a little while. So that natural pressure that it's under, we want to use that. But that's going to give us a really good idea of how things are moving along, right? If pressure is very, very steady, we're in a good spot, right? That tells us there's probably a lot of oil in this area, that it could be very nice to keep drilling. We might even want to drill additional wells. If not, maybe we start thinking about bringing pumps in. Maybe we start looking at this and saying, yeah, we got oil, but it's not a very good well to use in the first place. We might not want to invest any more in this than we already have. So this is a very fun link. It's kind of wild, to be honest. I don't want to show it here because, of course, posting this on YouTube and everything else, then I'm just watching some other video, and I'm going to be as silent as that video is. The animations in this are from some company that was, you know, an informative infographic with these little animations showing how these different processes worked. And I think what they did is they paid somebody to go through every single animation and voiceover as necessary. And that means you've got like 2-minute long stints of silence. A little bit awkward to watch by yourself, a lot of fun to watch with a friend. So I do recommend it. It does show a few more things than what I've got here, right? They do a good job of actually showing a lot of the different varieties of wells that you might see. So highly recommend, but I think for now, we're going to call this here. We will pick back up next time with the 4-2 lecture. We will close out this chapter, finish off our discussion about oil here, and start talking a little bit more about what it means to have the fossil fuel economy that we do today. But until then, have a good one, and I'll see you again next time.